Okay. All right. So far in the chapter we've learned about galvanic cells, and then at the end of the chapter, what we're starting now, we're going to talk about electrolytic cells. So tell me some things you know about what we've learned so far, and we'll decide if they go in the middle or if they're just about galvanic. Ashley? Two half cells, all right? Let's put that in the middle. That'll go with both. Two half cells. All right, now I want to say something about how those are different and the same in relation to two half cells. So there's going to be two half reactions in a galvanic and in an electrolytic cell. Okay, both of them are going to have two halves. In a galvanic, though, they're going to be in two containers. So that's what we've seen so far. We got beaker 1, beaker 2, metal 1, metal 2. They're separated by the wire. Then we got the salt. Okay? In an electrolytic, though, they will be in one container. All right, something else? Salt bridge. Okay, galvanic salt bridge. Because you've got two containers, so you got to keep those charges balanced. But in the electrolytic, no salt bridge. Yep. Yes, and you have an anode and a cathode for both. All right, what happens at the anode? Okay, so that's going to be the same in both. Oxidation is still going to happen at your anode, and at the cathode, still going to have reduction. The wire is present in both. And what flows on the wire? So far, pretty similar, other than the container part. On the galvanic, how do you decide which one's the cathode and which one's the anode? The one that flipped. How do you know which one to flip? The lowest one, okay? And so when you flip your lowest one, your voltage turns out to be positive. So in a galvanic cell, you're going to have positive voltage. But in an electrolytic cell, that's not the case. And you can't just flip the low one, because in an electrolytic cell, you're going to have negative voltage. So a galvanic cell, when we say positive voltage, that means it's producing current. So we can say that it is a battery. A galvanic cell. Those ones that we've been looking at so far. Those are producing current. And the amount they produce depends on what metals you use. Right. In an electrolytic cell, though, it's negative voltage. That means it needs current. Or needs a battery. So to make these work, these electrolytic cells, you got to plug them up either to some source of electricity or to a battery. Very good. The galvanic, because E is positive, it will be spontaneous. Then the electrolytic is going to be, and remember we talked about spontaneous occurs without outside force. Non-spontaneous is going to require outside force to make this happen. So what does that mean about our delta G? On the galvanic, delta G will be negative because it's spontaneous, and here delta G will be Which way do our electrons flow? Anode to cathode. So that's still true. Alright, in a galvanic, your electrodes, your metal electrodes play a key role. But in the electrolytic, usually your electrodes are just a place for electrons to flow through. Because it's what's in the solution that's going to matter in this case. Not really what's on the metal strip. Okay? So, in this sort of cell, you'll often have what we call inert electrodes. And you can have those in galvanic too, but they're more common in electrolytic to have inert electrodes. Just some random metal that's going to conduct our electrons but not really react. So the main difference that you want to keep in mind is galvanic produces energy, electrolytic requires that energy. So here's a picture of an electrolytic cell. This one's got copper and copper. So copper on both ends. And then the solution is blue, so it must be a copper solution. And they're just going to run electricity through this solution. So this is some very large battery, and then you can set the different parameters. So you can change the amps, you can change the time, you can't change the volts, I don't think. Amp, time, yeah, those are your two things. And you can change all the notes. Yes. What happens is you choose your battery, so you just choose the voltage by changing it like on the whatever battery you're using. What's going to happen though is when we measure voltage, instead of saying this is how much voltage we're going to make, it's going to be this is how much voltage we're going to need. So like say we calculated that you needed 3 volts, but your battery that you're plugging up only had 2, nothing's going to happen. So when we calculate voltage for electrolytic, it's going to be voltage that we need to make something happen. Okay. Whereas on galvanic, that's the voltage that we're going to make. So this is going to be voltage that we need. All right. So we're going to look at the simulation, maybe? Where'd my mouse go? All right. So just copy this in your notes. This will be probably a new page, depending on how big you write. And then put the helpful information in a little box. And I can make that font bigger. Yes. Then, yeah. All right, so we can treat this much like a mole map when we start to do electrolysis problems. Okay, so we can solve for all sorts of things like you see there. So if we're starting in the top left corner, we've actually done this calculation before. Current in amps times time will give me coulombs, okay, or charge. So that's what you see here. Current times time gives me coulombs. Anybody remember what does our time have to be in? Seconds. All right, once you have coulombs, you can find moles of electrons using this, 96,500 coulombs over 1 mole of electrons. And you may have to flip it depending on which way you're going on the map. So if you're trying to find moles of electrons, you would flip it over. If you're trying to find coulombs, you can use it like that. Right here? Faradays. So a Faraday is at 96,500. All right, once you have moles of electrons, you can go to your moles of substance, meaning like copper, silver, mercury, okay, whatever your substance is, using N, and that's just talking about a mole to mole ratio. And so like 1 silver over 2 electrons. Okay, silver wouldn't take 2 electrons. 1 silver over 1 electron. Or 1 zinc over 2 electrons. And 1 mercury over 2 electrons. We wrote that down? Yes, yes, because they were used in, and it was those electrons. Good. All right, and then if you know moles of substance, like if you know moles of silver or something, then you can go to grams, and this is atomic weight or formula weight. What's that talking about? Molar. The atomic weight, formula weight, molar mass, those are all the same thing. Alright, so this is just like the mole map where whatever's under the arrow is telling you how to get from one place to the other. Okay? But it's not as detailed as our mole map because I'm trusting that you can figure out which way to flip stuff to get it to cancel. So let's think about the simulation that we ran. If we look at our simulation, we should be able to find amps from what we set it on, right? And then where would we get time from? Okay, whatever you set the time on, right? But you would change it to seconds. So we set our time on 40 minutes. So we would do 40 times 60. That would give us seconds. And then we had 3.5 amps. So 40 times 60 times amps, that would give us coulombs, right, or charge. Then there would be so many coulombs, so we would need to flip this over so coulombs could cancel. Okay, that would give us moles of electrons. All right, we were using copper plus 2, so how many electrons did it need? 2, right? Copper plus 2 needs 2 electrons. So we would do copper over 2 electrons. So our electrons would cancel. And then we got moles of copper, and then we can go to grams of copper. And it should turn out to be 2.74, because that was the change we saw on the simulation. Okay? If you ran zinc with the same amps in the same amount of time, you would get the same number of moles. But you wouldn't get the same grams. Why not? Different molar mass. Okay, so you'll see that when you do type of metal tomorrow, that as you change the type of metal, you're going to change the amount of mass you get just because they have different molar mass. All right, let's look at a couple of these on your sheet. Example 1. Ma'am? You probably want to cut it because they're two different things. All right, the current in a given wire is 1.80 amps. How many coulombs will pass a given point on the wire in 1.36 minutes? Okay, we're looking for coulombs. If you look at the map, what two pieces of information do we have? Okay, amps and time. So here we see that amps times time gives us coulombs. Okay, so this problem should be fairly simple. On your helpful, did y'all get to write down the helpful information box? Okay. So here on the helpful information, we see that an amp is coulomb per second, and per is telling you like it's a fraction. So an amp is a coulomb per second. That's how you get seconds to cancel, so you're trying to get to coulomb. And I'll pick up a yellow sheet from right there. So when you write amps, this is something that I guess we'll just have to memorize. 1.80, I'm not going to write A for amp, I'm going to write coulomb slash second. Then I got to figure out this. So go minutes to seconds, how? Okay, 1.36 times 60, so 81.6 seconds. So I set that up like that. Seconds cancel. Yes. As long as you have top and bottom. Good question. 81.6 times 1.80. 147 coulombs. Yes, because that's all they asked me for was coulomb. So I just did that very first step. Okay, amps times time is coulomb. So I talked about this before, but your power company is charging you by the coulomb. Okay, so if you have something that's a real low amp device, for example, charging your phone, that's not a lot of amps. Okay, so it'd be amps times time is going to give you coulomb. But your hair dryer pulls a lot of amps, and your clothes dryer. So the longer you run those, amps times time, that's going to be more coulomb, so it's going to charge you more. Okay. Same thing with like if you try to plug up a lot of stuff at one time. Like you can have your computer, your TV, your phone, all that plugged up at the same time. That's fine. You try to run, like I did yesterday, the heater and the hair dryer at the same time, you're going to flip the breaker. Okay, because the breaker is set up the same way on amps. Okay, but then they're charging you per coulomb. That makes sense? Okay, so amps is how much it pulls per time. All right, example 2. A constant current of 8 amps. What am I thinking when I see amp? Okay. 8 coulombs per second is passed through a cell containing zinc, positive 2, for 2 hours. How many grams of zinc will plate out onto the cathode? So we need to go from amps to all the way to grams. Okay? So the first thing we're going to do is amps times second. Okay, so 8 coulombs per second times, how many seconds do we have? Okay, how'd you do that math? 120 minutes. Okay, 120 minutes, that's 60 plus 60, okay, 2 hours, 1 hour, 60 minutes, okay, or you could just do 2 times 60, 60 minutes per hour, and then times 60 again. 60 seconds per minute. Okay, so ultimately we have 7, 2, 0, 0 seconds. Alright, seconds cancel. Alright, instead of stopping, let's see if we can keep going from here. What do we need to get to cancel now? Coulombs. Alright, and if we look at the map, what number goes with coulombs? 96500 coulombs. What goes on top? 1 mole of what? Okay, so very important, 1 mole of electrons. So our coulombs will cancel. Now we need moles of electrons to cancel. Alright, so when you get here, when you want moles of electrons to cancel, think about the charge on your metal. What charge does zinc have? So how many electrons is it going to take? So we got 2 electrons to give me 1 regular zinc solid. Because right now I have zinc plus 2. So if I want zinc solid, it's going to take me 2 electrons. If you're not sure, some of them are a little more confusing than others, look at your voltage chart and see how many electrons are in the half reaction. Okay, so for zinc, there should be 2 there. 2 electrons for every 1 zinc. Yes. Okay, so we'll look at the same things we've been looking at here, like it says zinc will plate out, so I know it's zinc solid, and then zinc plus 2. I know the one that has plus 2 and solid in it. What? Okay, electrons cancel, but now I have moles of zinc, and now I want to go to grams. Okay, so what do I use to go to grams? So moles on the bottom, 1 mole. Molar mass, yep, 65 grams. So moles cancel. And now I will have grams of, which is exactly what I was looking for. So if you will use your unit, you can tell if you set up the problem correctly or not. So 8 times 7,200 divided by 96,500 divided by 2 times 65. Divided by 2. 4. I got 368, so 19.4 grams of zinc. Cathode, that should be how many grams you lose from the anode. As long as the anode's zinc, not the anode something else. Then change. Alright, now what they'll do on multiple choice with these questions is, obviously, you can't do math with 96,500 on multiple choice. Okay, so your choices will be setups. Like one choice will be 8 times 7,200 times 65 over 96500 times 2. Right? So the top numbers match and the bottom numbers match, that's the right answer. Okay, then if they don't match, then it's not the right answer. So do your setup, then look at your choices and see which ones match. So what they'll do is on one choice, they'll put the 96,500 on the top. Okay, but that would be wrong because we need to divide our electrons. If you're going this way on the map, if you're going that way on the map, everything would be. Okay. Calculate the amount of time. So here we're going the other way. Calculate the amount of time required to produce 1,000 grams of magnesium by the electrolysis of molten magnesium chloride if your current is 50 coulombs per second. We're going backwards. So we're starting with, okay, you can't start with amps because you don't have seconds, okay? Because amps, coulomb per second, the only thing you can do good with that is go to coulombs, but you gotta have seconds, you don't have that. So we'll start with 1,000 grams of what? Okay, so whenever you write a number, you have two things following it, a unit and then a identifier, grams of magnesium. So we need grams to cancel, So what cancels grams? Alright, magnesium. I'm going to put 24.3. Okay. And then what's going to be on the top? That gives us moles of magnesium, but we want moles of electrons because we're talking about amps, so we need electrons. All right, so magnesium on the bottom. Now, can you see here what the charge on magnesium is? 2. So how many electrons do we need? The magnesium cancel. Grams of cancel. Good. 1 mole of electrons on the bottom, and then 96500 what? Coulomb on the top. Okay, so moles cancel, electrons cancel. Now I got Coulomb. All right, you can do this 2 ways. You can stop here and then use your amps, or what's an amp? So it's 50 C over seconds, right? So we can flip it as seconds over 50 C. Whew, this is going to take a long time. There's no negatives in here. Yours what? That's what I got here. 15. I'm going to go 9, 1, 2, 3. 159,000. We can divide by 60. So this is seconds. So we can divide by 60. So that's 2,600 minutes. So we can divide by 60 again. 44 hours. So about almost 2 days. Alright, y'all know how you can send in your baby shoes and get them covered in brass? Okay, so that's what they do. They're going to put your baby shoe down in this electrolytic cell. They're going to make your baby shoe the cathode. Okay, put the brass or copper in the solution, hook up the battery, electrons are going to flow, the copper is going to plate onto your baby shoe. Okay. Also, if you have like spoons or forks or different things like that that are like copper plated or silver plated, like they just have that on the top, you know, it's not all the way through. That's the way they do that as well. Make that the cathode, run the electricity through, and then it'll plate on top. And it should plate pretty evenly, and then they just get a thin layer and then unhook it. Okay, the longer they leave it on there, the thicker the layer will be, but the more money it will cost. All right, do this one and then be done. What's that? Yeah.